often I go several months without updating R or do it at the start of the semester or start of the school year. But maybe we could install R and library of that and update R, and could be a possibility for doing that.
Yeah, it's just a library tomorrow.
Is that how? Is that
VFDA systems and mass, so different fun.
I did that go through.
So that's what went well. He's heard back. They told me here like this week or next week. So
Would that be like right on the interview?
yeah, yeah. So like if my phone interview goes well, then I'd have to go down there for a full day of interviews.
Okay. So what I wanted to do today is look at the data for this example that we talked about. Right? So I'm thinking about approaching a complex problem. Sometimes it's good to just step away from the data and think about the models that you might do and what the elementary data would be, and then think about, do you really want to summarize it into kind of summary statistics before analyzing it, or do you want to try to build a model that actually does that? So we did that on Monday, kind of think about the range of models that might account for treatment, might account for time, and what we might have ideally for an analysis. More characteristics. This data analysis, this problem in there involved monkeys who were taught words, to recognize words or symbols and pictures at different times in the past. And then an experiment was done where there were some control monkeys that nothing was done to them, and others, they actually blocked some of the functioning of the hippocampus in the brain to study memory, things that affect memory and understand functioning of the brain. An experiment that might not be done now. It has, its rationales for understanding brain functioning and what you might do if somebody's injured or has a stroke. But anyway, so the book approach summarizes the data and then analyzes it, and that's fine. Many people would proceed that way, but we're trying to build models that account for the elementary data, which is essentially success or failure on each of 100 words for every month. Right? So we're going to do that. I'll post a homework, a problem on chapter 16. I was kind of investigating a couple that are in the book, but really maybe the example, the case study there would be something to work through in some more detail. We talked about projects. There is a project presentation at this, and I've been left that document that I was going to edit on my computer here. I didn't come in because of the storm, so I'll get that updated and posted. But it's very much like the same idea. They can be joint projects, presentations on a topic, and likely, be desirable if they go a little bit further than the other ones. Use some methods from recently in class, or take some of the methods and then just do a larger analysis and learn more. Yeah.
Just to be clear, at the project, you're presenting that on our final exam time?
Yeah.
Okay.
Yeah. So the final exam time, they schedule 2.5 hours for that. With the size of the class, there'll be plenty of time for everybody to present, have 15 minutes or more, if you really have some things to do. Many academic conferences give you 12 minutes or 15 minutes to present. Invited talks might be 20 or 25. If you interview for jobs, often you get 45. Some seminars, some places are a little bit longer, but generally mini conference proceedings are 10 minutes, 12 minutes, 15 minutes, which is, I almost think about it as an advertisement. Right? You can't necessarily get into the full details of a year-long research project in that amount of time, but still you try to communicate main ideas and why it's interesting and some sense of what you did. And for ours, if it's analyzing one data set and applying some models that are kind of familiar to the class, maybe you can talk a lot about what you've done in that time. Not necessarily mentioning everything, but just particularly the highlights. So I'm going to use my laptop for some packages. There's a question about updating R. Every once in a while, some packages that you have need to be updated. There is a package for updating R. Right? Out there, there's an install R package. So if you install that one in a library and update R, it should update to the next version. Often I've just, it's been so long since I've updated, I started the school year or the semester, just kind of install a new one, and that's fine, but then you have multiple versions of R on there. Going through the installer one might be preferable. But so if you do encounter that as you're using R for a longer period of time, it might be, there are ways to do it. So let's see, what do we want to look at? We want to look at this R here, right? So, go back up to the start. So, we're going to use this case 1601. Oh, here's how I modified it for the printing, and I've installed it and everything. And so it has extra variables on there right now. So let's just see the version that I ended up with here as this. Now the original data set did not have these short and long columns. It had the monkey's name, controller treated, and then their score, their percent score at the different weeks. Each of those weeks has 20 words that they're tested on. Apparently every monkey had complete test results for all the 20 words every time. So they had 16, and these were the scores. Right? And so these are words that they learned 2 weeks before treatment, and then they're tested after treatment. Or they were taught words 4 weeks before treatment, and then they're tested after treatment, and so on. And some of the words they were taught 4 months ago. So they went through the training exercises on those at 16 weeks. So these are in the past. So these would be remembered, they believe, through short-term memory, right? Something that's happened within the last month. And then these would be remembered through longer-term memory. Or, there's kind of a gray spot where it is short versus long. Go in there. These are the average so the short term, these are the average of these two. Right? And this long one is the average of those three there. So that's the data that's reported in the book. And they analyze that. But what I want to do is look at, well, each of these numbers is really based on 20 yes, no, correct, false answers. We could recreate a data set that has all the answers in it. Now, we don't know. I can't recreate the order in which the questions were. Maybe within 20 questions they start out really good and then they kind of drop off, so there's kind of order effect there. I can't tell because we don't have the raw data. But if you had the raw data, you could see do all the performances kind of drop off as you go along. So to set that up, I'm going to set up a data frame. Right? So I'm going to put the monkey's name 100 times each. So this rep or repeat command can be really useful for doing some of these things. So repeating numbers. Okay, can I get? Here's my cursor. So repeating, say the repeat command. Say if you have the number. The numbers 5 and 6, and you repeat it 3 times, it'll do 5, 6, 5, 6, 5, 6. Right? To repeat that pattern. If you put 2 numbers there like that, right? Repeat will repeat. It matches it up. It does 5 3 times and 6 3 times. And you don't necessarily have to have these things be equal. Right? You can have 3, 5, and 4, 6. So it's a very flexible command for doing those things to help a repeat. That will show you some of that. So this one will produce the monkey's names 100 times each in a row. I've attached the data set so I can just refer to it. So the treatment, each monkey is in one treatment group, so it's repeat their treatment. So treatment has 18 levels. Monkey has 18 levels. Right? And then they are tested on 5 weeks, 5 different time periods, right? 20 each. So 2, 4, 8, 12, 16, 20 of each of those. And then that whole thing gets repeated for every monkey, right? So 5 times 20 is 100, and then 1800. So that sets up this this thing that we call DAT, right? And so DAT, if you click on this over here, just on the object, it brings it up. So as it is now, it says the monkey's name, treatment, control, and the week. That's there. So that's setting up this data frame. So you see the week changes, and after a while, we get the next monkey, and control, and things like that. A little while to get that right. And then we're going to put the percent. Well, I don't want the percent at each of those things. I want 1 or 0. I want to reproduce the 1s or 0s. And so we have this data set has, I don't know if I can do it so well, has, pop back up here, has week 2 data, week 4 data. So really the column it's in has kind of indicate what week it is, right? So a variable, what time period has been put into the variable name. Right? That complicates things. Generally, you want to avoid doing that. People do that all the time. They'll give you data, and an essential item, like what week it is or what treatment group, is encoded in the variable name. So it's kind of necessary to break that out. So we've created the week variable that has all of those weeks in there. I was given one, sometimes people put critical information like that into the ID name of the object. It'll be like Chim2, like the monkey Chim in the 2nd week. And so that extra piece of information, which should ultimately could be a variable, is now part of the name of that row. So you kind of have to do some manipulation to get that out. So I'm going to bind all those weeks together. You could just kind of select that as part of the matrix. And so this just kind of puts it all together there. So that's those numbers. T is a matrix transform. And so I'm going to tilt it on its side. And then I'm going to make it a number. I'm going to take off the matrix structure. And the way it does it is it goes by row. Right? So I want all the week, no, it does it by column. Right? So I want all the results for one monkey, and all the results for the next monkey. And this kind of like manipulation gets me that. So this thing will, right, produce this thing called percent. Percent is just this list. And so the scores for the first monkey are here. For the first 5 are the first monkey, and then the next monkey, and the next monkey. So it took a little bit of manipulation to get it to match up like that. The percent is 90 long, because it's 18 monkeys, 5 time periods, 18 times 5. I can convert these percents into right or wrong. Because I know that each one had 20, so I can take 20 times the percent over 100, and that'll give me the number of right and the number of wrong in there. So right and wrong are these. So right is listed as the number of the right, this is the number that the monkey got wrong. And so by pair going across there, they add up to 20s. I added them together. Right plus wrong always adds up to 20, so you do little checks in there to try to make sure that this has worked out. If you bind those together, so you have kind of, and then transpose it again, you get 19-1, 15-5, 16-4, 13-7. So this is the first monkey in the first time period, got 19 right and 1 wrong. And then the next time period got 15 right and 5 wrong. And so it's a little manipulation to get that matched up. And then I'm going to go through and just create a y variable that's either 0 or 1. Right? And I was trying to do that more automatically, but it didn't, for some reason I was getting a funny count. So I want to create something that's 1,800 units long. Right? And I want a certain number of ones, a certain number of zeros, a certain number of ones, a certain number of zeros. Right? And so this is my little code to do that. Right? I'm going to initialize it all at -9. Right? -9 is not a number I can use for 1 0. Right? And so that'll if I don't end up using all of it, right? I'm going to start a counter, just a dummy counter at 0. And I'm going to go through the 90 elements of right and wrong. And I'm going to go from increment by 1 up to the current count plus the number of right at that time period and make it 1. And then I'm going to update my counter to the end of that period, and then take the next one up to the number of wrong and make that 0. It turns out that all the right and wrong are not, none of the wrongs are zeros. If some of them were zeros, you probably have to check. It might give you an error. Right? If you could put it, if right sub I is greater than 0, then do that. If wrong sub I is greater than 0, then do that. Right? You could put that in there, but it's not necessary in this case. So this little thing creates a variable y in there, so it runs through. And I try to do it, I thought I should be able to do it automatically, but I don't know why it didn't work. The thing that it gives you are some 1s and 0s. It's good to do a check to get the percentages. If you calculate the percentages in a way, and then compare these to the table in the book, it matches up. It has done something where here's a PO, it begins here. So numerically, 12, 16, 2, 4, 8, because 1 is the first digit, is before 2, and so on. I often like to put things 0, 2, 0, 4, 0, 8, so if I put them in order, it just keeps it in that numerical order. I find that useful for files and in computing and so on. But anyway, that's there. It's good to look at example rows, do checks that it matches up. So here's oops. Go through there. Or if you look back at DAT, has that updated? Oh yeah, it's been added there. This Y has been added there. Right? So there's a bunch of 1s and 0s corresponding to that, and it matches up to what the summary data would give. Now in reality, you probably don't get all 1s and 0s. I can't recreate that because I just don't know. Some of these are early, right? So that's a function of weeks. So I can create a 1 for early, and then if the week, that whole column is less than 8, wherever it's less than 8, I'm going to change it to a 0. Right? So there's probably a single command, like an if-else type of thing to create that, but I find that just as easy. So now we have our variables. We have treatment and early, and we can do an interaction. And we could try to predict y. Now y is 0, 1, so that's not the best for using linear regression. We would really use logistic that we'll talk about coming up pretty soon. Right? But you can predict it. It's still going to do a least squares fit. And if all the variables are there, let's see if we're good. Right, we get this result. Treatment, the interaction is highly significant. Treatment versus early. So if a monkey is in the treated group, they score better on the early words, or that's the interaction. The early ones were learned longer ago. Right? So they're more long-term memory. Right? But it has these effects. So early, those kind of balance, I don't know. Treated generally scores lower on average. The words that were learned early had kind of a lower average, longer term memory. But there's this interaction that's there. So I think, anyway, it gets that R squared, even though all of these are highly significant, R squared is pretty small. We get 0.1 or 0.1, so it doesn't predict very much about the pattern. But it is significant. There is some effect there. We have 1,800 observations. This treats them as independent, because it's just a linear model. Right? And some of the monkeys score higher, some of them score lower. Some have changes probably in their patterns over time of how they do. And so that would not really be the best model to fit to do a summary, because it doesn't capture that repeated measures structure. Right? but it is 0, 1. The alternative that instead of that 0, 1 model is something called generalized linear model, or GLM. GLM is just part of the standard package. You don't have to, standard R, you don't have to load anything. And so it looks much the same, treatment, early, and then an interaction. That's the data set. And it has a family command which tells it what type of probability distribution are you fitting. And the binomial is the one that you use if it's a 0, 1 outcome, right? Gaussian if it's normal, right? And there's some other options. And so it gives estimates, standard errors, a z-value compares to normal distribution, and p-values. And again, it's same significance. These coefficients have slightly different meaning. What the generalized linear model is doing, switch back and forth. The generalized linear model is the y variable is 1 or 0 with some probability. And it looks at the logit of the probability, right, and relates that to some coefficient. So we have treatment, indicator, the early indicator, plus treatment times early. So instead of doing our y outcome, it kind of relates this average or expected value on this transform scale. This is called the logit transformation. And so this is a form of logistic regression. We will be talking about this. It's in 2021, something like that, in the book. So we will talk about how this gets estimated and things, but we get these estimates of these coefficients that are in there. Once you have those estimated coefficients, you can convert it back to the probability scale. The probability, if this is just called theta, then e to the theta over 1 plus e to the theta is p, and 1 minus p is 1 over 1 plus e to the theta. So there's a way to go back from this linear scale, that's the linear model part, back through the transformation to your original scale between 0 and 1. And it's called generalized linear models. The generalization is that you have this thing over here, which is kind of a link between the expected value of y, between p and the linear scale that's not necessarily linear. It's a transformation. And so the meaning of a coefficient is a little bit different. This is a log odds ratio. And as a treatment or a variable over here changes by one unit, it changes the log odds. Right? And so it has actually a multiplicative impact. Right? E to a parameter, imagine all of this up here, as you change something in treatment or change between groups, it changes something up here in the exponent. So it's like multiplying. So it's kind of a multiplicative effect on the odds. But we'll go through that. That's kind of what it's doing. It's more appropriate for 0 or 1 variables that we've created. But the commands and the output looks very much like linear regression. It's just, when you interpret it, you just got to think it's a little bit different. But any questions? We'll go through that in more detail with the model. But for 0 or 1 variables, so it gets significance. A reason for doing this is that the y hats, just from the linear model, might go outside of 0 or 1. But this one, because of the transformation, keeps everything on an appropriate scale. So it all makes sense. Right? These things don't get evaluated in terms of R squared, but there's something called deviance and AIC as an information criterion is useful. So all those are significant, right? But these analyses really haven't taken monkey into account. And that is kind of the source of repeated measures, because each one of these is on there. So some of them might be high. So there could be a correlation between how they do on one question versus another question. So you could just put a fixed effect indicator in there for monkey. And you could just add that to the linear model or the generalized linear model. What's the problem with doing this? It's 18 monkeys, right? So you need 17 coefficients added onto that, right? And there's only so many variables, so many possible values, and it turns out that some of the monkeys have exactly the same scores, early versus late. So there's the whole output for it. Right? You get all these coefficients, they don't really look significant. It has problems estimating for one of the monkeys. That could be kind of similar scores to the other one, or maybe a combination of 2 or 3 monkeys. Could be collinear, so it kind of has a little numerical problem there. R squared doesn't go up that much. The conclusions about early versus treatments and so on are still there. And you get the similar type of issues with generalized linear model, that the output, you get all these coefficients. Now these are the multiplicative ones on the GLM scale, but you still end up with one of the monkeys having similar x values as, or maybe one is like the average of the other 2 or something like that, so that there's some kind of redundancy or problem there. Yeah.
Wouldn't in like this case, if we were taking a regular linear model, we can expect the R squared not to be a good estimation because it's like a categorical. So like if we take like a linear line between like the 2 sets.
It could depend on how things go. So you can get 0-1 outcomes. You can predict those well with the right x's. Right? So so if y here is only 0 or 1, and you have x's where there's a bunch of x's down here, and these people are all zeros, and these x's up here are all ones, that's going to predict pretty well. The residuals will look kind of funny because it has to have, there'll be a string of positive to negative and a string of positive to negative, so it doesn't really fit the assumptions. So you could get pretty good R squared.
Yeah.
In this case, our predictors really, if you have early versus late and treatment, and you cross those, at most you have 4 groups.
Yeah, like most of the times I feel like there's going to be a lot of values for x in which there's both a 0 and a 1 value, which is going to...
Yep. So if it was more, if you had it more, you had some of these people and some of these people, right? And this is 0, and this is 1, and these are the x's. And there's more of an overlap. I mean, all the line can do, right, is kind of go through those.
Yeah.
And it just doesn't work so well. And I think in this case, our x's, in this case, there's only really 4 groups. Early treated, early control, late treated, late control. So you're saying there's 4 proportions, and there's a lot of variability, so it just doesn't work so well, really, to predict that, right? I mean, the book, by grouping them together into percentages, tries, instead of getting 0, 1, if you take 20 questions together and turn it into a percentage, you get more variability this way. You get kind of more pattern. So a regression, 2-sample t-test compared on the percentage is correct at different time periods or different, right, could be better for that. It's closer to the model. Maybe not perfect, but it could be something like that. So yeah, you can get high R squared. We don't get very good R squared. In this case, we'll talk about AIC later. So an alternative is repeated measures. And so a mixed model where we have a random effect for each monkey that induces some correlation, like we talked about last time, across the measurements. Right? And it's in this LME4 command, which is a library that you can load. And so the linear mixed effects model regression is LMER. The other command looks about the same, but this is how the monkey is intercepted. So at the intercept, the first thing there's an effect for them. Right? So those are given a random effect, a normal distribution on the effects of those, and this is the output that comes out from running that. And I think I have that still operating. Yes, it's still operating. Good. And it tells you what it did. There's a few different ways to do this. So initially, it doesn't give you these p-values. The people that wrote the LME4 package don't like p-values or numerical approximations, and they'd rather simulate everything, I think. So they don't like putting it on there. There is another package, maybe it's down here, LMER test. So some other people said, well, we'd actually like to have p-values associated with those, so I'm going to write a package that uses yours and does something to get p-values. They use something called likelihood, kind of a profile, so they find the points that are on the kind of 95% intervals and see if zero's in them. And they get a p-value associated with that. So what comes out of this thing? Right. They get something like residuals, scaled residuals. They get random effects. Right. So there's a monkey random effect and a residual random effect that's in there. So this would be an estimate of the sigma for the monkeys. There's very little variation among the monkeys after you take into account treatment and early and the interaction. The measurements of these, there's some, it's either yes or no. So the standard deviation of the residuals is about 0.5. Right? So if the percent correct would be 0.5, you'd have some residuals that are 0.5 and some are negative 0.5. And so the standard deviation of those kind of ends up being like that. But it is kind of group. They're more successful than not. So it is kind of up there. And so anyway, you get the estimate of these two random effects. And you get estimates of the fixed effects. Now this is on the linear scale. So these are just, you increase, about 18% correct in this group with adjustments. So you start at 80%. If you're in treatment, you take away 17. But in early, you kind of recover it. But if it's not early, you don't recover it. If it's this, if you've got 80%. If you're not in treatment, then you are lower on early. Otherwise, you're about 80%. If you're in control for the longer term memory, or the questions that were asked longer ago. It doesn't give p-values, but you can look at the t-values. They're -4, -3. Those are pretty large, right? Whatever t-distribution you use, it's going to be about -2 or +2 for a 95% cutoff. So these are going to be significant. If you use that LMER test, you get the same results, except on the fixed effects, it actually adds p-values, which are small. Consistent with all the other models. There's a significant interaction and significant main effects. With random effects, you can look at the random effects. These things are the random effects by monkey. So you can see that there's little differences after, there's a treatment effect and the early late effect. So that's already taken into account. But beyond that, there's not all that much difference between them. They're kind of performing at a similar level given which group they're in. Right. You can do that. You can also look at the fixed effects, just gives you those there. And there's a function to do confidence intervals for any of these things. Right? So we have confidence intervals for the intercept or the treatment, the interaction effect. And so this is on the linear scale, so we can think about those just as confidence intervals for the parameters. Right? Adjusting for the autocorrelation due to the repeated measures within the monkeys. So it's taking into account that to some degree. Right? And you get estimates for the two variance parameters. Now this, the one for the monkeys, ends up hitting the boundary at 0. Right? So it's possible that there really is no variation among the monkeys, and they're taken from a more homogeneous population in terms of their ability to do these questions. But that's modeling something 0, 1 with a linear model, which might not work out so well. You can do that. There's a generalized linear mixed effect regression, so GLMER. Right? It looks just like the linear one. This statement is the same. It's GLM, the generalized, because of that logit transformation. And you tell it that it's a binomial family. So this is indicating that the y variables is 0, 1, and it does that particular logit transformation. Within the binomial family, you can do that logit link But there's other links that could be done as well. But the default is logit. What reminds you of that there? And the results look very much the same. These models, in terms of AIC, BIC, or likelihood, that's how you compare models. In this, it says there's a little problem, right? It says something about singularity. Well, this monkey intercept is the variability of the different ones are very, very small. Right? After you take out the effect of, there is variability among the monkeys, but after you take out the effect of treatment and the interaction with early versus late learning time periods, they come out pretty much at 0. Right? So it's maximizing a likelihood, and that thing kind of it happens to have a peak that kind of goes up towards 0. So it gets kind of stuck over there. Some people try to do things like Bayesian analysis, can put in prior information to kind of pull that away. Some people put a lower bound on that, says no, it should be at least 0.001. Let's make that the boundary so it's not at 0. But it's kind of hard to deal with. It's just a fact of fitting the model that there's very little variation in the monkey scores after you take account these other factors. So it just warns you it's at 0. Still, it gives the tests for these, I think, would be reasonable to report. There are big effects. There are some correlations between fixed effects estimates. In ordinary linear models, there's correlations between the estimates. The intercept and slope are not really independent. They're both functions of the data. And you raise the intercept, you kind of tilts the slope to try to fit the data so they would interact with each other. But anyway, same message, very, very similar, right? If you take out interaction, you kind of run into the same problem. It's not a matter of fitting the intersection, and so this is just a little snippet. If you take out the estimate of the variance on the monkeys, it's just really, really small, near 0. That's there. So what could you do? I would still report the analysis. But with the data formulated like this, we can look at, just the general weak effect. Right? Instead of just classifying it into the learned early, learned late, long-term, short-term memory, the weeks were 2, 4, 8, 12, and 16, so we can put that in the model. Right? This formulation is linear. Right? Is there a linear increase in learning over time? And if you put that in, weak is significant as a predictor, right? And it looks like it has a negative value here. There's a positive interaction. So, what can be done to show you that? Later we have some graphs, but anyway, you can put it in there as a linear effect, right? So changing from 2 weeks to 4 weeks. So this coefficient here is about 0.05, and you kind of want to do that. So let's consider a control monkey, right? So that the treatment doesn't interact there. So we can let's do this. Look at what the fitted values are. Let's see if this will work. See what these things are. The fitted should take it back to the original scale. One more maybe. Right, so there are 10 right. So there are, in this model, there's 10 possible outcomes, right? Or combinations of predictors, right? So there's 5 weeks, 1, 2, 3, 4, 5, and there's treatment or control with a full interaction. So you can have 10 values. So 1, 2, 3, 4, 5. That should be 10, right? And when it's early, there were 7 individuals getting treatment. So 7 times 20 is 140. So the control ones, I'm sorry, there are 7 in control, so that those ones pertain to control, and the 220s, there were 11 in treatment. So these are the predicted percentages correct under that logistic model. So you might want to round those to, there's some variability, 63, 64, up to about 73, 79% correct is coming out of that model. And with some effort, you could figure out which one they exactly correspond to, which levels. Right? There's an interaction, so weak generally has a negative effect. So the longer you learned it ago, at 16 weeks, you have less memory than at recent, unless you're in treatment. And then there's kind of a reverse process, right? There's a big drop in terms of treatment, but you recover some of it in the long-term past. Which gets at the hypothesis, does interfering with the hippocampus affect the long-term or the short-term memory? We'll try to look at that. But another way to do weak, right, is as a factor. Because maybe it's not linear, and maybe it's not early versus late, but maybe it's more up and down. So let's create a factor variable. I'm going to put the levels in order, 2, 4, 8, 12, 16, so it's easy to tell what they are. And then if you put, you could put factor of week in here and factor of week in there, but that's kind of cumbersome as a formula. Plus I want the levels to make sense to me. So I created a new variable. If you run this one, it gives. So that boundary, again, the variance of the monkeys accounting for the other things was pretty small. Right, the treatment is, you would look at these, now the interactions, now there's 10 parameters, including the intercept, because there's 5 levels interacted with treatment control. So all 5 can be different. So now you've jumped up to this many parameters. Some of them are significant if you just tested these. Right? So there's some things. And it looked like, so weeks 4 and 8 are not significant, 4 and 8 are not significant. So I thought, what does that mean? Maybe early versus late shouldn't be, the ones that we learned recently at 2 and 4 weeks in the past. Maybe the cut point is 8. Or maybe 2, 4, 8 should go together, and 12 and 16 should be separated instead of the other way. Right? By having this individual data, you can kind of test these things, I think, a little bit more directly than otherwise. Right? So that's what I was kind of worrying. Thinking about, so we could create a new early variable that just put 12 and 16 together. So learning it early, with just putting 2 together. If it's less than 12, it will be 2, 4, and 8. We get to base 0. So that's slightly different from the other one. So we're going to create that variable and fit some different models and compare them. Right? We can look at AIC, BIC to see which models we preferred. Right? So this one's linear. Right? Week is linear, so a certain impact by weeks. Right? This is where the weeks are split in early and late, but with 2 of them being early. This is the original one where 3 were early. So 16, 12, and 8 were together, as learned long ago. Right? And this is with the factor, so that it's all 5 levels. Right? So actually, these first 3 have the same number of parameters. They're just using the data differently. Right? Because it needs 1 slope for week and 1 slope for the week at the intersection. Right? This one just has 2 levels of that variable. So again, it's 1 coefficient right there. The week, though, had more. And we end up with this as AIC and BIC. Right? And what does it look like? It looks like the original model, this E3. One gets the lowest values of these things, right? That says that splitting early and late, like the book does, according to this, makes a little more sense than the other grouping. And we don't need to go to the full factor because there's some similarities at 12 and 16 and similarities at 2 and 4, right? That we don't need the full flexibility. And linear doesn't work so well, right, in comparison to these things. Linear is not linear over that whole time period, so linear is not preferred. So we selected a model to do this. We can plot, do some things, get fitted values, right? And so this is comparing two models, right? The full factor model with all 10 parameters, so 10 predictions. And the E3 one, that was the better one, with 4 predictions. What do the predictions look like? These are the predictions, and so the scores, right, in the original data were 70, 80, 60%, things like that. So these percentages are kind of in this range. This E3, right, has essentially 4 levels of prediction, right, treatment and early versus late, interactive. Right? Whereas the one with all the factors has 10 different levels, right, that go out there. And so this one is combined. Must be 2 levels, right? So this is one of the later ones, and so it's learned later. So it has 2 and 4 must split out here, kind of like this, and 2 and 4 must split out. If you do a little more work to put the numbers and labels and treatments in there with a graph to see a little bit more what it's saying. Right? So I created a little vector called color, so kind of treatment color. Blue for control, and then red for treatment. And then if I'm going to plot this thing, and this type equals no, we'll just set up the plot, but not put points on it. And then I'm going to put text. I'm going to put the day of the week, the weeks, 2, 4, 6, 2, 4, 8, and so on, and color to see what those things are. Right? And there they are. It's so bold because it's actually all 1,800 points, kind of what we're plotting again. So I don't know how to. An easy way to do that, but it's kind of interesting, right? So, okay, why do we have an interaction? So these are all the ones here that are learned in the more distant past, 8, 12, 16. Treatment and control seem to be about the same there, right? So affecting the hippocampus does not seem to impact the long-term memory. But this is short-term memory, right? And this red is treated, and this is control. Control does a lot better. So impacting the hippocampus really hurts the short-term memory. And, right.
Well, wouldn't it hurt long-term memory based on the plot? Because the values are lower?
Well, long-term memory is less.
Yeah.
Anyway. But this includes both the ones that are treated or untreated. So long-term memory is less. Right? That's a significant early versus
Oh, is
late.
the red the
Red is treated.
Oh, okay, I'm
And the
sorry.
blue
I
is
thought you said
control.
the opposite. I was so confused there.
Yeah. So anyway, that's kind of the summary picture that's there, right? And the advantage of an advantage of going into this modeling, well, in either case, if you had characteristics of the monkeys, male, female, age, experience, you could put that into any of the models. Right? But if you had information on the questions, like the question order, or the types of questions that were asked, like some are maybe objects, whereas some of those are pictures, you could possibly put that into the expanded data set. Right? You couldn't necessarily. Maybe you could do it in the summary data, but then you need to break out the summaries, and it would become more complex. So I think going back to the original 1 zeros, correct or not, gives you more options for doing that. What does the book do for analysis? Well, the data started with just week 2, 4, 8, 12, and 16. And then they averaged the ones that would be short-term memory, weeks 2 and 4, and then averaged long-term memory 8, 12, 16 together. And right, that's what those are. We could do a t-test. Is short-term memory different, treated versus control? And short-term memory, treated versus control, is significantly different. The treated group has a much lower memory recall of those. The long, the t-test of the long, as you see from that summary there, is not significant. Right? So, the book talks about Hotelling's t-test. Right? So it's a multivariate version of the t statistic. Right? Testing simultaneously, are there differences in the two groups on either variable? I haven't done this in any type of application, but certainly it makes sense in some cases there, and people that work in repeated measures maybe use it more. That's why the authors have included it. They must have used it in some of their applications. There is a package called Hotelling. Howard Hotelling wrote papers, and you install it and do library. And I'm going to break out the data that are the two variables, short and long, for treatment, short and long versus control. And there's a Hotelling.test. For packages, you can look at help of those. So there's help package equals Hotelling. Capital. There, library Hotelling. Let's see, help, oops, down there, help, say, let's see, Hotelling test. So yep, that's there, it looks like I looked at it before. 2 sample Hotelling's t-squared test for testing that. There's a t-test method, there's a simulation method, kind of like our permutation test method. This Hotelling's article was in 1931 in the Annals of Mathematical Statistics. These are a couple things, or this one is about that issue of estimating zero variances, I think. Right? Shrinkage approach, large-scale covariance matrix estimations. Right? So if you run that, it doesn't give you a whole lot of information. It gives you the test statistic, and a numerator, denominator, p-value. So it's implementing what the book does, right? But it doesn't give you a lot of insight into where the differences are. And I'm not an expert on this package, so maybe there's a way to do what they do and get more. But it looks like they've made a lot of specialized graphs to try and illustrate things. I don't know how to do those specifically. If you simulate it, it has a nice little bar to mark your progress, 10,000 simulation, and it gives you a simulated p-value. Right? I know I want to figure out how to do that for when I write some code that's going to run for a while, so I know what's going on. There we go. And it gets a plot. This is a simulation of the test statistics values, and an observed one is way out here. So I think the conclusion based on that is there is some difference between at least one of the means between these two groups. And we know from the individual t-tests, which would be like a contrast applied to this, that there's a difference of in terms of the short-term memory, because that is where the hippocampus seems to function, versus the long-term. So it gets kind of interesting what you can do with the variety of models and things that we would do. Thinking about things as factors versus linear versus subgroups of the variables, right? The predictors really builds on what we do with linear regression or what you might build on with ANOVA. We're going to assign some problems so you get to work through an example. It'll be involved using some packages, surely, to do the linear mixed effects models. And then we're going to go on and talk about some of the categorical data so that we get into logistic regression and see a little more details of what goes on there. So, Okay. See you on Friday then.
Oh, yeah. I just like them even more in class because like I'm just trying to get it done in time because you have to really rush it.
Yeah.
So like the only way